Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're gonna talk about element isotopes. This was requested in my synthetic element episode. So let's understand this very thoroughly. This topic goes very deep. The rabbit hole goes very deep. So we're just gonna take a surface level overview. Now let's start with the basic atoms. Now atoms are building blocks of element. Basically, if you want to understand an element, you have to understand its atom, and you cannot go any further than that. Now this is one thing that you must understand, that you cannot go below that. Because your first instinct would be like, hey, what about proton, neutron and electron? The moment you go at that level, quote unquote subatomic level, you no longer have any properties. That's one very important thing. Think of it this way. In biology, we also have the same thing. For example, cell is the building block of life. You don't say sulfur is the building block of life or carbon is the building block of life. You say cell is. Why? Because cell is living. The moment you go inside that, basically mitochondria or nucleus, it no longer is quote unquote living. You broke into a machinery equipment at that point in time. Same happens with here also. You can go inside an atom, no problem with that, but you could have a scenario where, let's say, you take one proton and you basically transfer it, remove it, and you will go from basically lead to something else. You can literally go up step, one upstairs where you have bismuth, or you can go one downstairs and you can have talent. So that's the whole reality of it. You cannot go any further than that. Atom is that level, like that's it. You do not go below that. Only then you can do chemistry. If you start to go, that's a different level of studies, but surface level, to understand elements, you have to stop at atom. That's one core important factor. Now we have lots of different quote unquote varieties, types of atoms. So to make our lives easier and to understand nature better, we created something known as periodic table. Now periodic table, you basically see a shortened version of that where you have this segment plonked downwards. The reason for that is basically it's easier to print in books and all that jazz, but again, this is the correct form, and you can notice that in every Wikipedia article about every element, they will generally have long form. So reality is, how the heck we gonna qualify something? There are a lot of types of atom. How the heck we qualify? We go into the center of an atom. Now in the center of atom, there is a nucleus. In nucleus, there are two types of things. One is neutron, another is proton. Now proton is charged particle, so it's kind of easy to study that. So we classified everything based on proton. So proton is denoted as a Z in some types of equation, and proton defines what you are. So basically, if you have one proton, you are hydrogen, you go into hydrogen category. You have two, you go into helium. You have six, you go to carbon. You have seven, you go to nitrogen. That's up to you. Fundamentally, that's what we are dealing here. Basically, your proton number defines where you get into the periodic table. Now periodic table does not only run on basically proton. It also has another data point, which is atomic mass, basically how quote unquote heavy it is. Now to achieve that quote unquote how heavy it is, you generally take the mass of basically proton and you add with neutron. Now proton and neutron generally carries the 99.99% of the mass of an atom. Now this is kind of completely different, completely struck different how people in electronics and in semiconductor industry view atoms, so to say. In their industry, electron is everything. You have to contain electron. You have to make sure the gate does not leak electron. In chemistry, electron is like, who cares? Is like periodic table does not even mention it. The reality is very simple. If you want to take a mass of an atom, basically, let's say you want to figure out this atom is 100 gram, how much is in electron? It's almost zero. So reality is, for mathematical reason and for multiple chemistry reason, you have to figure out everything based on nucleus, not on electron. Electron is secondary to it. Now to understand the size variation of here, basically how big an atom is, you have to understand how empty it is. To understand that, think of it this way. You take a football stadium, that's your atom. If in the center of it you have a very small grain of basically basically something small, a pebble, that would be nucleus. Most of it is empty space. So how the heck we interact? Strong force, weak force, and all that, magnetic force, all that jazz. That happens on an atomic level. So atom is completely empty. Now even though all the mass is focused on the center, and that's the whole reason why neutron stars are so dense, is simply because they do not have empty space. So they go from like one tablespoon weighing around few billion tons. That is the reason for that. So most of the categorization, basically the whole periodic table, is focused on nucleus of the stuff. Now size wise, you also have to understand, even though they are very tiny physically, they are ludicrously dense. It is the densest form of matter known. And then Even if you take nucleus and you strip its electron, basically you force it into what we call fourth state of matter, aka plasma, it will still retain its property. For example, what will happen if you plasmify helium? You'll get a different kind of color go. What happens if you do that with neon? You will get neon signs. What will happen with argon? You'll get different colors. What happened with krypton? Again, I'm pretty sure some luxury cars have that as a bright white light source because it's surprisingly good with that. Sometimes xenon are also used because xenon, while it's not quote unquote white, it is much more pleasant kind of blue. So that's completely up to you, and you can understand all these are happening in quote unquote plasma state, yet they have their own properties intact. That's why nucleus is so important. You tamper with electron, nothing much changes, but the moment you tamper with basically proton or neutron, you end up in different place in periodic table. So that is very critical. We are always focusing on nucleus of an atom, and it's everything focuses on nucleus basically. And in nucleus you value proton more than neutron because of its charge nature, and based on that we have decided that everything is gonna in a periodic table is gonna be based on proton numbers. That's a very important dial. Like basically when you see 5, 6, 7, 8, 9, all these are talking about proton numbers, how many protons they have. That is the surface level, that's just the basic of it. Now let's understand isotope. Now you have to understand that once we actually became good with chemistry, we went from like, okay, we made a periodic table, it has a lot of empty space. The places where supposed to be things are supposed to be, like basically we found something, let's say number 10, we did not find something number 11, but there was 20, 12, 13, 14, so we left an empty space for it. That did work. That's how our first periodic tables were made, and it is true, holding true till this day. But reality is, once we actually started looking quote unquote deeper into things, we realized different elements have kind of quote unquote cousins. For example, we know hydrogen. Now hydrogen has a basic state which we call basic hydrogen. It is basically hydrogen 1 1. It has basically one proton and one electron, normal Dr. Manhattan symbol. But we also started to find something very interesting, basically where you had hydrogen, it has one proton, so that's why in hydrogen category in the periodic table, but it also had one neutron, so basically the atomic mass went to 2. Then we had another variation where you had still one proton, but you had 3 basically atomic mass, simply because it had 2 neutrons extra. So what the heck, we did not classify this as an independent element because we had when we are making periodic table, we qualified that protons are the primary number. So all these things became a kind of quote unquote z-axis. Basically they are variation of that primary element. So primary element in this case would be hydrogen, and everything else would be classified as isotopes of hydrogen. You have to understand. And now you may be like, okay, why did not deuterium or tritium ended up in the periodic table? The reality is, the way periodic table was made was based on very simple things. It was like, you have to find that isotopes normally. Basically, if you go there and you do mining, you find carbon. But here's the deal, you will find carbon 12, you will find carbon 13, and you will find carbon 14. But here's the deal, most of the time when you do your experiments, you will be always experimenting with C12, because whether you like it or not, carbon 13 and carbon 14, they are not stable formats of it. So even if at the creation of solar system there was enough carbon 14 and 13, it will not have lasted. So at this point in time, most of them would be in the lower state of carbon 12. So carbon 12 was the first thing we studied, and that is the way we are filling up the periodic table. It's like, it should be like, you go out there, you mine that element, what is the natural state of that is put in your periodic table. So that's the whole point. Now all these periodic tables, generally what we have, we can understand one thing, they are stable, otherwise they would not be there. Basically C14 is not very stable, that's why it's not abundant, it's not in the periodic table. C12 is. So different isotopes, quote unquote, different quote unquote neutron variations could have different, drastically different life, basically how long they live as a completely intact atom. Now when you're talking about on an atomic level, it's hot, let's say it's very high unbalanced. Basically what does that mean? That simply means, think of it this way, do not think atom as a mass, think of atom as a condensed form, basically quote unquote solid form of energy. Now you can understand that some format would be very much more stable, some would be unstable. So how the heck an unstable atom, like basically in vacuum where it cannot bump to anything, how the heck an unstable atom supposed to cool itself down? It has to do that because it's unstable. How the heck is going to do that? Because everything in nature, does not matter it's in vacuum or like in a sea, under or inside a planet core, it always wants to reach a lower energy state. How the heck it's supposed to dump that energy? Enter radiation. So everything that is quote unquote unstable, it will utilize radiation as a way of dumping excess energy, basically going from unstable state of, let's say, carbon 14 to stable state of carbon 12. Same will happen with tritium, deuterium, and everything. Basically if it's unstable, it's like, bro, I need to dump my energy and I need to calm down. How the heck is going to do that? It's going to utilize radiation as a mechanism. It's like, okay, let me radiate away some energy. Now, and that is another critical aspect. That's why different elements could have drastically different lifespan if you're directly comparing their isotopes. For example, you can start with C14 and basically C12, like if you want to compare that. Now, everything in periodic table will decay over time, but here's the deal. Some numbers are so huge, basically, like if you want to wait for how long a proteum will last, it's like, 1 to the power 10 to 37 zeros. It's ludicrously long. We don't even count that. So those ludicrously long are classified as quote unquote stable. So basically, if the number is too huge, we classify as stable. So carbon 12 stable for every single measuring purpose. That puppy is stable. But C14, that does not last. That only lasts 5,700 years. Now you may be like, that's long. No, not really. Like if you go that same basically how far we have to go for pyramid, you invert that time. Like basically go from pyramid, take a string, just push that string in the future, you'll be like, yeah, all the C14 is gone. So reality is C12, while it's carbon, stable, while C14 still carbon, not stable. So how the heck C14 is to like basically quote unquote calm down and start to live longer, it will become radioactive. And that's the basis of basic carbon dating. And same will happen with hydrogen. You can have deuterium and tritium, both of them have a half-life of around 12 years. So basically they do not last. They go from like billion year lifespan to like 12 billion if they are at unstable state. So half-life becomes an important kind of scenario. Now half-life is not something that we may figured out. It's like how nature behaves, so to say. So nature behavior is very simple. You take 100 liter of, let's say, C14. After 50% of time, you will have 50 liters. Now here's the, you may think, okay, if half-life is that, it like, in X amount of time, I'll go from 1 to 50%. In the next two, basically X2, I will go to 0, because again, I lost 50% in the first go. That's not half-life. That the half-life is halving of whatever you have. So basically you start with 100 liter, you go to 50 liter. Now you have 50 liter in X2. You end up with 25 liters. Now you have that. Now you end up with 12.5. Now you have that. You will end up with like 6.25. Now you have that. You end up with 3. That's what we call about half-life. This is very critical. Do not think like if you go 2 times, you go to 0. You go from like 100% to 50% to 25% to 12.5% to 6%. Things of that nature. Now unstable isotopes are, all they are doing is basically giving off energy. That's why I specified, think of atom as a physical format of energy. It's like, I cannot contain this energy, I have to give it off. How do they give it off? They utilize radiation. So they can achieve neutral state, basically where numbers of proton and neutrons balance it out and they become stable. That's the one core thing. Now particle decays are the first method that an atom will employ. It's like, dude, I'm too hot, I need to calm down. This is the first method they will employ. They will basically create a whole another atom inside and they're just gonna eject it. Just like, go away, I don't want to talk to you, just go away. For example, alpha decay, like you hear about this, like alpha radiation. What does that mean? That simply means the nucleus of an atom is like, bro, pack up basically two neutron and 2 proton and just eject that. So basically it's if you're gonna take this element on a periodic table, it will literally jump 2 steps below, because it's gonna lose a 4 of mass and 2 of proton, and it's gonna eject a helium ion from the inside. Basically the nucleus is ejecting helium ion directly. It's like, go away. That's alpha decay. And because it's a complete atom, that's why it does not have quote unquote penetration power, because it's a very heavy and it's like it can't go through other stuff. So that's why you will hear people say things about like a sheet of paper can stop alpha radiation. That's the core reason. Now basically the atom is now a much cooler state because it's directly dumped. Basically it went from periodic table, let's say position A, to -2. Basically it went 2 steps downwards. That's how alpha radiation is dumped. Now alpha radiation is a huge dump. It goes like 2 steps down, like you are dumping a lot of energy away. But what happens if you did not have that kind of energy? It's like you had a lot of energy, you are still unstable, but you had to dump a little bit of energy. You will do that with beta decay. Now beta decay is kind of interesting because beta decay is a kind of incomplete kind of transition, where it's like either a neutron or a proton goes YOLO. Basically a proton can say, you know what, I don't feel like it, I want to become neutral. Or a neutron can say, I don't feel like it, I can become a proton. So what will happen in that scenario? Basically in both scenarios, you are inverting something neutral or something charged. Now it will eject an electron. Electron is very little in mass. That's why I specified electron is like nobody cares in periodic table, because it's so little mass. Like even though it's changing a whole electron, it's not doing too much. However, if a proton changes state or a neutron changes state, you are changing the charge value. Basically you are changing the element number. So if a beta emission happens, you had the electron left, it will literally go from basically one step below or one step up. So if it lost basically negative charge, basically electron that came out was normal electron negative charge, it will become positive. Basically one neutron became a positron, a positive charge. So you will have p plus 1. What does that mean? That simply means periodic table will go 1 left. Basically it's adding up. So you will go from C6 to 7. But what happens if basically proton wants it to become neutron, basically wanted to lose a charge? You will have positron. Basically that's how we figured out there could be antimatter. This was the first step of us realizing that it's still an electron, but it's in like a positive direction, charged positive direction. Your mass is not changing. Be mindful. That's why I specified electron has no mass. It's like not changing anything at all. Like again, if you go down 0 0 0, there is a mass change, but practically it's 0. But your proton is no longer the same number. So your proton could go from 6 to 5. Basically if you are releasing antiproton, you're going backwards. If you're going normal electrons, you're going forward. That's how you're happening. Basically we are changing a neutron into proton, go ahead, because your number changed. Now you are in a different periodic table, basically a different element group. And if you are basically removing something else, basically your proton fields does not feel like happy, and it's like I want to go down, it can go down also. So that's one electron jump. Now because the electron is much lighter, it's much more penetrating. Basically it can penetrate much further than a sheet of paper. However, aluminum sheet can easily block it, and your dead skin cell on your front basically surface can easily block it. However, if it goes inside you, you did. Basically if it's inside you, there is nothing inside your body that can protect against this. That's why you can be poisoned with beta radiation. Alpha you can handle that, but beta, good luck with that, you did. Now what happens if you are still low energy? You were talking about like little bit of energy excess. What will happen then? Photons will be used. Basically energy is there, energy is in there in a weird kind of format. Basically the energy required to hold the atom together itself is a format of energy. Itself is acting like it. You cannot count that, but it is there. There is energy there. How the heck you stabilize that? You dump it in photons, and that photons will be in gamma radiation spectrum. It's a very high energy photon, almost unstoppable, because A, it's photon, it's very small, and B, it's ludicrously charged. So it's very, very powerful. Charge as in like energy wise, I do not mean as in like positively or negative. It's non-charged. That's why it can go through anything, because it's not going to interact with electron field or proton fields, because it's just going to go through things. But it's damn near impossible to stop gamma radiation. That's what when we are talking about when we are talking about half-life and radiation. Basically atoms are not in stable state. They want to reach a stable state, so they can have like a whole atom ejection from their core, they could have an electron ejection from their core, or they could just have basically photon ejection. In photon ejection generally changes do not happen. It just will go just like in chemistry there will be star mark when it's a radioactive, there will not be a star mark if it's non-radioactive. Mass change is almost negligible in this. However, mass like element changes will happen if you are talking about beta radiation, and in alpha radiation there like 2-step changes will happen because mass is changing. Now this is the decay chain that we are talking about. Now every element fundamentally changes over time. You have to understand this, and you have to understand it very thoroughly. Every element is there. However, if some numbers are too huge, basically like hydrogen, it's like few billion hextrillion years, we're like count it as stable. However, there is a bigger brother of periodic table that we call NZ graph. Basically you take neutron, you add them in one axis, you take proton, you add them in another axis, and then you draw out graph. Basically every isotope figured out. It creates another kind of quote unquote periodic table. Now this periodic table is much more fuller because it accounts for every single state of element we have found so far. To give you how magical this puppy is, think of it this way. You started with uranium 235, everything is fine and dandy. It's like uranium is like, I don't feel like it, man, too much energy, I need to dump some. It dumped off a freaking helium. Now what happens after that? Now the energy level went down 2 steps down, that is thorium 231. Now what happens that it's like, dude, I'm still not feeling like beta emission radiation. Okay, step 1 down, another alpha radiation, another beta radiation, another alpha, another alpha, another alpha, another alpha, another beta, another alpha, another beta. Now it has come down to lead 207. Lead 207 is very stable. So that's these things happen. Now you have to understand, even though I'm showing this whole chain, it does not mean like it happens continuously. It's like okay, 5 minutes from this to this to this. Like it could literally be weird where it will like this jump that happens like in milliseconds. Like you made the reactor in basically reaction, first few reaction you got that, in second reaction it's like changing that, then it can be like idealing in one state, and then it's like it's gonna take its few million years to go to lead. So that does happen, and that's why this periodic table is kind of important, quote unquote NZ graph. I have provided basically its extended form in Wikipedia. Try to have a look at it. Be mindful, it's very long, very, very long. So it's the granddaddy of basically periodic table. This is what people study when they are talking about basically they want to study stellar evolution, because stellar evolution allows us to understand how the heck Big Bang created these elements, how the heck supernova creates this kind of element, because they never create like quote unquote lead. They are too high energy. So what would they create? They will create uranium, but uranium will decay into lead. So these sort of things happen. So to understand this whole quote unquote how the heck we got such a stable kind of periodic table, you have to understand this puppy AZ graph. And when I was talking about basically synthetic element, the elements that we humans are creating in labs, we are trying to achieve what we call basically island of stability, basically where it's as stable as uranium. So we do not know. We may achieve it. We may have vibranium or some other magical stuff. We do not know, but we are working on it. So that's the decay path, and you have to understand. I provided links down below and videos down below for further research. So this was my presentation, a surface level of isotopes. I hope you liked it, learn from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike. Press it twice to show me extra disappointment. Please leave a comment because I try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.